Thank you, Stephen. I'm Satrajit from Aarhus University. I'm going to talk about TinyOLE, which is actively secure two-party computation from oblivious linear function evaluation. So this is a joint work with Nico Dotling, Jesper Busch-Nielsen, Tobias Niljes, and Robert Trifletti. So first, our starting point is the arithmetic 2PC. We are working in the settings of arithmetic two-party computation where two party A and B, they want to compute some arithmetic circuit C in a secure fashion. So the party gives their secret input X and Y in the protocol, and after the end of the protocol, they'll get some value Z. So it requires that the protocol to be correct. That means that C of X, Y must be equal to Z. And by privacy, we mean that one party will not be able to learn any information about the secret input of the other party. Or in other words, that the parties will learn only the output of the computation. So we are considering static malicious adversary. That means from the start of the protocol, uh, one of the party is malicious, and it will remain malicious up to the end of the protocol. So this is definitely a settings for dishonest majority. So it is well known that computational assumption is necessary in order to get some kind of meaningful security in these settings, and there is no guaranteed termination. So if one party uh, one party get that one other party is cheating, that it will just abort on the protocol. So but as computation assumption is necessary, then these protocols are not very efficient. So how to get a efficient protocol in these settings? That we can use some preprocessing model. So in preprocessing model, it consists of two phase, like offline phase, where the party will do some interaction to generate some correlated randomness, and in the online phase, they will compute the actual circuit using those correlated randomness. So usually the offline phase is input independent and also function independent, and but this contains all the public key operations, and hence it is the expensive part of the protocol. Whereas in the online phase, the parties, given the correlated randomness, the parties will evaluate the circuit in a get by get basis in an information theoretic manner. So what I mean by correlated randomness, there's two kind of correlated randomness given by the offline phase. One is random authenticated value. So the the offline phase give one party some value R and the MAC over that value, and the other party some global key delta and some verification key K, such that M is delta into R plus K. So it's clearly this kind of MAC is linearly homomorphic, means that if you add two MACs like MR plus MS, then that will give a MAC for R plus S. So I use here a simplified notation box in R, which means that R is a authenticated value. So the second kind of correlated randomness is the random authenticated multiplication triple, which is actually used to compute the multiplication gate of the circuit. So in this case, the offline phase gives a some authenticated value, AA, BA, and CA, and B some other values, AB, BB, and CB, such that CA and CB is the additive share of the value A into B, where A is A plus AB and B is BA plus BB. Now, given this kind of correlated randomness, one can very efficiently compute the uh, circuit in a online phase. So all the secret sharing based schemes more or less use the similar kind of online phase, and this is really efficient. For addition, given the authenticated shares, you evaluate the addition gate by locally add the shares. And but for multiplication, you need to de-randomize the random authenticated triples. For that, it's usual to use Beaver's trick. So the addition gate or the linear gates of the circuit is computed locally, and for the non-linear gates, you use Beaver trick. Now, the main challenge is that how we can implement offline phase in a more efficient manner. So there's been long work in literature. For example, there are schemes based on homomorphic encryption. These two are not the only schemes. There are many schemes, but like there are schemes based on homomorphic encryption, like Damgard et al. Gives the SPITS protocol, which use homomorphic encryption to compute the um, multiplication triple. But for malicious security, they need uh, some expensive zero knowledge. So that's why these protocols are not very efficient in practice. There is another approach is to use oblivious transfer to do the same job. So Nielsen et al. Proposed the TinyOT protocol, and there is a long line of work after that optimizing this kind of protocols. But they use essentially OT to do the same job. But this protocol, these OT-based, all tiny OT-based protocols are for binary circuits. So in last year CCS, Marcel, Emanuela, and Peter proposed a protocol which gives the first actively secure protocol in a OT-based settings for arithmetic circuit. So now, what we are doing in this work, we give a protocol which use oblivious linear function evaluation. Now, so in a nutshell, we give a actively secure 2PC protocol from oblivious linear function evaluation. We use OLE as a black box. That is important. Then you can use any efficient instantiation of the OLE to make a actively secure efficient 2PC protocol. And also this, our protocol is very simple due to the black box use of OLE. Our protocol is unconditionally secure in OLE hybrid model. Apart from OLE, we didn't use any other fancy primitive. So the whole protocol apart from OLE is information theoretic. Communication-wise, we get some constant communication overhead, which use some order of OLE per multiplication gate. And given the recent constructions of constant overrate OLEs, we can get a order of like constant overrate OT per multiplication gate. So in a concrete sense, we require 22 OLEs per multiplication gate for active security. So yeah, I want to mention that there exist general compilers like IPS or AMD-based compilers, which can be used to give same kind of results from OLE. But for their general description, it is really hard to compare that with our results. Though we try to give a hand-waving comparison in our paper, it doesn't seem that the constants are smaller than the constant in our case. So when we instantiate the OLE with a recent constant overrate OLE protocol by GNN17, we can see that we get a good communication overrate per triple. For example, like speeds give 430 kilobit per triple, mascot gives 360 kilobit, and in our case we have 180 kilobit per triple in a field size of 120 bit, 28 bit. It's important to note that we get statistical security of 128 bit, where speeds, I think, achieve 64 bit statistical security in the same settings. Now, what is OLE? As I mentioned like several times, OLE is the oblivious linear function evaluation. So in this protocol, there are two parties, one sender and one receiver. The sender will give some A and B into the protocol, and the receiver will give some value X. And at the end of the protocol, the receiver will learn Y, which is AX into plus B. And from the security point of view, as usual, the B will not learn anything about A and B, and A will not learn anything about X. Now, given that, I will explain step by step that how we get actively secure protocols to generate the multiplication triple. First, I'll show how to generate passively secure multiplication triples from OLE, then how to authenticate those triples, and then I'll show how to check the consistency of the passively secure protocol. So, so what we want in this phase? So we want to instantiate something like a offline phase, which gives some A, BA, and CA, AB, BB, and C, so that this equation is satisfied. Now, the party A choose some AA and BA randomly, and B choose some AB and BB in a random fashion. And then now just expand the equation a little bit, where these blue terms correspond to the party A and the green terms correspond to the party B. If we expand it, we can see there are some blue terms here, some green terms here, and there are some mixed terms. So these blue terms can be computed locally, or like the same color terms can be computed locally by each party. But for these mixed color terms, both the party have to interact. So how we do that? Just introduce some random offsets, say RA by the party A and RB by the party B. Now, if we can rewrite this same equation in this form. Now, if you see closely, again, this blue color term like A, BA minus RA, or here the green color term can be computed by both the parties locally. But for this cross term, they can use actually OLE. How? Take an example for in case of A. So A give this BA, like blue BA in the FOLE, and B gives AB and RB. Then the resulting term will be the same, like AB, BA plus RB. So now he can locally compute the shared CA from this thing. The B can similarly compute the local shared CB. So in this way, they can just compute their shared CA and CB. So our protocol now looks like that. Both the party use two OLE calls to get the multiplication triple, like passively secure. Now, how to get like max over these values? Again, we can do a single OLE calls for each of the value. So say A want to compute a MAC over the value A, so it will input A in the FOLE, and B have the global key and the verification key, it will input in the FOLE, and it will get the MA, where MA is equal to A into delta plus K. So A will compute the MAC for all its local value, and also the share CA, CLA, and whatever he have, B also do the same symmetrically. So now we have triples, and we already have max over those triples. So the protocol looks like this. First, they will compute the cross terms, then they will compute the max using some OLE calls. Now we have to make sure that the protocol make sure the consistency of the inputs in this protocol, to get the actively secure authenticated triples. What I mean by that is that A can definitely can have some local AB, which is this blue CLA, but he can input some say red CLA in the MAC to get some other red CLA. Similarly, a malicious B can do something like that. So B is supposed to input same global key in all the Mac instances, but she can input some red delta in some of the instances. So this kind of deviation from the passively secure protocol that can be maybe that can used to leak some non-trivial information in the online phase. So we don't want that. We want that they follow the passively secure protocol. So we need to check the consistency of the inputs in the all OLE instances. So we use a method which is, we call it fingerprinting. So intuitively, fingerprinting is something like that, like each party have many local values and also many intermediate values computed in the passively secure protocol. So they will use those values to get some value uh, which we call fingerprints. Now both the party can compute these fingerprints, and at the end of the protocol they will check the consistency of the fingerprints. Now take an example. Say A has some value A, B, and AB. It's the local shares of A, and he want to compute the MAC MA, MB, MAB over these values. And B has some uh, global key delta and the verification key for these MACs. Now the goal for A is to ensure the consistency of delta, and goal for B is, say, for in this example, to see the consistency of AB with A. Now, how A is computing the MAC? Just for recall, A gives this AB to the OLE instance, B give delta and K in the OLE instance, and then A compute the MAC MAB as AB into delta plus KAB. Now, given that, so how A can check that whether this MAB is consistent? So if he can somehow compute MAB in some other way from some other MAC, then he can claim, or he can check the consistency of both the values. So one way to do that, like A has this MA, which is previously obtained, say MAC on the value A, which must be some A delta plus K A. Now, if you multiply this with B, that will give some AB delta plus B into Ka. Now, if you get rid of this Bka and add this Kab, that's give a different way to compute the same max. Like if delta is consistent, this max must be the same. So, but uh, A can compute this BMA locally. For this term, he needs some interaction. So again, he will use just OLE, one OLE call, and then he can compute MAB. Now, if these are the same, these max are the same, that gives ensure the consistency of delta. That ensures the consistency of delta. So, but there is a problem. The problem is that here this OLE can leak some information about the secret values Ka and Kab. So in that case, B can add some random mask, red gamma, in the OLE instance to get some value, which will be minus Bk plus Kb plus gamma. So now with the same computation, A can compute like MAB minus M prime AB should give some gamma not equal to 0. So the thing is that if gamma equal to gamma, then B uses consistent delta. Why is that? Just look at the equations a little bit closer. Say B use a delta prime in the computation of this MAB. Then this term MAB minus M prime MB will have some offset like this, like AB into the difference of two deltas. Now from the point of B knows this value delta prime and delta, but he don't have any idea about these values A and B. So this check, like gamma, or whether red gamma is equal to blue gamma, will fail with overwhelming probability in the field size. So that So this check actually confirmed that B uses consistent delta in computing MA and MAB. The same check in the similar manner can say that whether A uses consistent AB. Again, look closely. Again, this term contains some red A prime, and this MAB minus M prime AB will contain some mixed term, where this delta is not known to A. So again, this pass will be failed if A used some wrong A prime or wrong A prime B in this place. So that's it. So this gamma is known as so we call it this fingerprint. So both the party compute the fingerprint and check the fingerprint to see the consistency of the protocol. So, after both the party compute several fingerprints for different Welle instances, and then at the end of the protocol, they check the consistency of all the fingerprint using one single Welle call, using some global check, and that's it. That's gives the actively secure authenticated triples from Welle. And so overall, the protocol looks like this. AB computes some cross share using some Welle. Then they will compute the MAC. So this is a passively secure protocol. And then to make sure that this the consistency in the passively secure protocol, they will run this fingerprinting protocol for all the instances of this kind. And then at the end, they will run some global check to check that whether all these fingerprints are correct or not. So in summary, we give a actively secure 2PC protocol from Welle. This is a very simple protocol. Use Welle in a black box way, unconditionally secure in Welle hybrid model, and it has a communication efficient. So it requires, as I said earlier, the 22 Welle power multiplication gate, but we actually further optimize this to 14 Welles. So this is a ongoing work. So thank you.
One question, you're relying on this OLE functionality. I'm not familiar with it, so can you explain roughly how those work, or at least what tools it uses?
Yeah. What is this?
Yeah. So, like the protocol itself, like what kind of tools does it use? Is it symmetric key, public key?
To implement the OLE functionality?
Yeah.
But for our protocol, we don't need that how it is implemented.
Yeah, I'm just wondering.
Okay.
You're going to have to implement
So
it.
the
So how fast is
instantiation
it?
in GNN, they use the passively secure protocol, which is given in the IPS 08 paper, and they make that protocol actively secure, which use OT, which is secure in OT hybrid, and use some noisy encoding assumption.
Is it many rounds or few rounds?
Yeah. It has many rounds, but it's like five or six rounds or something like that.
Okay. And then another question: is this only apply to large field size
Yeah,
elements?
definitely. As you see in the proof that the probability will be negligible when field is large, so that's applicable for.
So this would not be useful for binary circuits.
Yeah. Thank you.
Hi, just a quick question on your complexity analysis. You
Yeah.
say you use 22 invocations
Yeah.
of OLE.
Yes.
Is that roughly the same analysis of mascot that comes down to like 11 sort of two-party multiplications? Maybe I'm not really sure if that's asymmetric, symmetric. Like you look confused, so I guess the answer is you don't see the direct link.
For one party, use 22 Welle invocations to compute the actively secure.
So basically, my question is just like, did you take anything from the mascot analysis and just apply it, or is it completely independent analysis?
No, it's just straightforward. You can just see here, like that's 20. That's 2. There are 5 max you have to compute. Then if you see the paper, there are like 3 fingerprints where you have to do 5 values. In this way,
Okay. So that makes the answer no. Okay, thank you.
Yeah.